everyone. We're live. So I'm going to share we're going to map out the week real quick. Zoom. There we go. So this week we're going to be doing quadratic equations, quadratic functions. Now, I know it seems a little confusing. This is going to be 3, 1, 3, 2. I'm taking components from each one, and then we're going to be laying the groundwork for quadratic equations. And then tomorrow, I'll be pulling out some of the same items. So really, homework 5 is going to be recognition of quadratic equations. What is the constants? What are some of the main components? And then day 2 is going to be solving quadratic equations. So we're going to be doing some factoring. We're going to be doing some, I would say, quadratic formula a little bit. No completing the square, but mostly how we're going to apply them to applications. And if we get a little bit of a hit today, I may sprinkle that in at the end of class. We'll just kind of get a feel for how things are going and how we feel, okay? And then we're going to roll into some calculus-ish, where we're going to be looking at the rate of change, but the rate of change in respect to horizontal change, specifically horizontal change of 0, which could be problematic if we think about average rate of change or rate of change with a denominator of 0, because can we divide by 0? No. So there's going to be a little bit of a issue with doing that. So we have to find ways of getting around it. Okay, then next week we'll roll right into some derivative rules. Lillian will be taking the helm that week and kind of improving upon my instruction by fixing all the things I've done wrong. We'll see how that goes. I think she'll do a good job. And then we finish up with exponential functions and finance. That's essentially it. Okay. So without further ado, let's go ahead and jump into chapter 3. And I'm going to do chapter 3 a little differently than I have in the past. This kind of worked for us last week. And what I want you to be able to think through is, I want to first, let's just dump everything we know about quadratic equations on a page. Okay. And then we're going to fill in the blanks in between. So instead of kind of like stepping into, okay, this is the quadratic equation, this is the identities, I want you to tell me what you know. Tell me what you know about a quadratic equation. Again, it could be anything once I mention those words. Okay. Just come on.
I would say the quadratic formula.
Okay. So quadratic formula. Does anybody know what the quadratic formula is?
It's x equals negative b plus or minus, and then in radical b squared minus 4ac over 2a.
Okay, so you want to say that one more time, Thomas?
Yeah.
Not wrong.
So yeah, it's x equals negative b plus or minus, and then in a radical b squared minus 4ac, and then that's all divided by 2a.
Very good. All right, very good. So there's our quadratic formula. Thomas, I'm going to give you bonus points today because most people forget this little nuance, x equals, because that tells you why we have this formula. Okay. So what is A, what is B, what is C then? And I'm opening this up to the whole class. Again, we may not know. That's why we're mind dumping to the page. We got to fill in the blanks. What else do we know about quadratic equations and quadratic functions? What are some of the things that we know?
The slope is squared.
The slope is squared.
Or one of the numbers are squared.
Okay, so
X is squared.
Okay, x is squared?
I mean, it doesn't have to be X.
So there is something squared, is what I'm hearing, right?
Yes.
We have a square, which in Bart says something is squared. The X is squared. Good. So we have an X squared in a quadratic function. Very good. Okay. Keep going. What else do we know about a quadratic function? And again, this could be anything, y'all. This could be what it looks like. What's the graph? Things like that. What do we know about quadratic functions?
It's a parabola.
There we go. Or as we say in the deep south, parabola. I say that jokingly, but in a way I don't, because that's how I remember how to spell it. Parabola. Okay, like geometry. Again, you're talking to a guy that just was not great at spelling, so he had to say it the way it's actually the way it looks. So parabola. Because you would say paragraph, not parallograph. Am I wrong? Am I wrong? No, like, oh, that's a head scratcher. That's worth thinking about. So parabola. So what does that graph look like? Not all at one time. Y'all talking over each other, it's just rude. It makes me sad when you don't talk up in class. However, when people answer, it makes me happy. You like that little segue, Lillian? So we have something that looks maybe like this. Spencer, yes, no. Parker, Sophia, Thomas, Ivy, George.
Yes.
I'm hearing a yes. Thank you, Spencer. I got a thumbs up from George. Okay. Julia's Duchess the Cat's just like, I'm keeping my eyes closed and I'm humming to myself. I'm having a great time. Okay, so we got a parabola. That's the graph. And so this is all we know about quadratic functions. Nothing else. Here's the thing, put it out there. It may be wrong, but we'll adjust it. There's probably some validity to what you're saying. Like, what are these A's, B's, and C's? Got a chat going on here. I think A, B, and C are coefficients. I'll take it. They are coefficients. Very good. Okay, so what coefficients are we pertaining to? Let's look at the base form then. AX squared plus BX plus C is our function. Okay, I'm going to put f of x. Keep in mind, the input is still x. The output is still going to be y or f of x, depending upon how we want to look at it. Okay. Our coefficients are specific items within this base form here. Okay. Now, linear functions were a lot easier because you're like, oh, mx plus b, m's a slope, that's rate of change, cool. The y-intercept was b. Now, please do not misconstrue this b as the y-intercept. That's not going to be the case. Okay, so let's dive into this a little bit differently. And I'm going to share a new screen with you. We're going to figure out what A, B, and C do through investigation on Desmos. Okay, can everybody see my Desmos screen? I love Desmos because you can create sliders and you could do so many different things. So there's a parabola. Notice my red line here, ax squared plus bx plus c. I have 3 sliders, okay, all at which are those leading coefficients. So the first one I'm going to play around with is a. I'm going to leave the other 2 fixed, okay? And I want you to watch what happens. So notice that A is getting what? Bigger or smaller? Is it increasing or decreasing? A, just look at the letter, just look at the letter over here. Look at the number. What's it doing? Going up or going down? You can point with your finger. I'm okay with pointing up or pointing down. And as far as the chat, I may not be able to see the chat entirely. So there we go, Emma, increasing, very good. Now, as it increases, what is my graph doing? Is it getting skinnier or is it getting wider?
Skinnier.
Skinnier, very good. Okay, so if we were to think about it in reverse, if A were to decrease, it should probably do what? Widen out, right? Let's see if that's the case. Okay, it's decreasing, decreasing. Okay. Well, yeah, so look at this amount, 0.6. It's a fractional amount. So it's pretty wide. Okay. The higher it gets, the larger it gets, the skinnier it gets. Now, notice what happens at 0. And I can zoom out and out and out and out and out and out, and guess what? It's just going to be a horizontal line. That's a pretty important piece to keep in mind. Now, not so much right now, but just keep this in the back of your head. But look what happens when it's negative. It has changed concavity to where it's now opening downward. Now, let's keep the same idea. Now, the more negative it gets, and I know that sounds weird, the more negative, like, for example, -2, -3, -4. So the colder it gets, if you will, it decreases, it's getting skinnier as well. So that's kind of tricky on our wording. What are we going to say there? Okay, so it flips when it's negative from when it's positive. So tell me what A is doing to my function. Tell me what A is doing. Let's try to summarize this. What did it tell us? If the function is concave up or concave down. We can start there. Concave up is up like a cup, positive, smiling. The current visualization on the board here is concave up. So concavity. So if A is positive, or A is greater than what? When I say something's greater, or excuse me, positive, it's greater than what? What do y'all think?
0.
Very good. When A is greater than 0, we are concave up. So if we are negative or less than 0, we are concave down. All right, so I'm gonna bounce back and forth to our handy dandy whiteboard. Okay. So just to give us a little bit more room, A is going to be telling us concavity. Excuse me. A is greater than 0, it's concave up. A is less than 0, concave down. Now, what else did A tell us? When you say the width of my parabola, when A got bigger away from 0, we'll kind of lay that out, like 1 to 2 to 3 to 4 to 5 to 6 to 7, concave up, it got skinnier. Does everybody agree with that? Now, does that work in the same respect in negative? So now, the more negative which is not increasing. So I really can't say when A increases, it always gets skinnier, because technically A is decreasing when it's negative, and it's getting skinnier as well. So how can we note what is going on here? And I'm going to introduce this little thing called, no, you know what? I'm not going to introduce the limits. I'm going to state it outright. Leland's smiling because she's like, oh, that's dangerous waters, sir. It's dangerous waters. So as A goes away from 0, okay, as A goes to infinity or negative infinity. So if we're having 0 kind of at the guideline here, we're talking about positive A and negative A. If they go from negative infinity or go to positive infinity, the further away from 0 it goes, skinnier it is. Okay. Skinnier the problem. Now, as negative A or A approaches 0, so coming from negative infinity, coming from positive infinity, but gets closer to 0, the wider the parabola. Okay, and we're going to go back to the Desmo screen to kind of help us illustrate that. Okay, so take another 30 seconds, write that down. Okay. So think about as A goes away from 0. So the more negative and more positive it gets, the higher it goes on my scales here. Away from 0, the skinnier positively or skinnier negatively we get. Okay. Now, as it comes from a negative infinity, positive infinity to 0, as it approaches 0, the wider our parabola gets. Okay. So take a look. As I get further away, positively, it gets skinnier but concave up. Further away from 0, but negative, concave down. Now, 0 is that tipping point where it goes from concave up to concave down. But look what happens when I get closer to 0. It gets wider, wider, wider. Like my curve is flattening out the closer it gets to 0. And there's a reason behind that. Okay, so notice I'm going to adjust this from, we're just going to say 1 to -1. Okay. So at 0.3, 3/10, pretty wide. 0.14. So the closer 0 gets, the wider the parabola gets. Which, if we think about it, the rate of change, if we were to substitute values in for x, you're multiplying it by a fraction. So instead of it going up pretty quickly, it's going to be a fraction of that amount that's being squared. So you're not seeing a huge output change there. Even though we are multiplying the x value by b and a c value here, we'll get to it in a second, you're seeing a fractional amount. Higher it goes, you're multiplying it by a fixed amount. Okay. When we get to that 0, look how wide it is at 0.02. You get to 0, flattens out. That's pretty important. Then it turns to negative. And it's a mirror image of what it would be positive. Okay. Now, why is that important there when it's 0? I don't know. So let's do this. Let's put it back to 10, -10. Let's shift our view away from concavity for a second, and let's look at to me, the next easiest one. That's C. Tell me what happens as I change C, as it gets larger or smaller. What's it doing? Is it getting wider or skinnier? Be careful. Emma, very good.
It's like if it's moving up or down.
Yeah, it's just moving up and down the what axis?
Y.
The y-axis.
The y-axis, very good. So what does that tell me then? If my C value is 3.1, it means it's crossing the y-axis at 3.1. If it's at -4.6, it's crossing the y-axis at 4.6. So tell me what C is in respect to this equation.
The y-intercept.
Y-intercept, very good. So that value of C is the y-intercept. Point blank, end of story, that's all it is, y-intercept. Okay, so obviously if you get it as it increases, as it goes up, it's just going to shift up vertically up the y-intercept. Nothing else will be affected here. Okay, when I say nothing else is affected, obviously the outputs will change. Okay, however, the concavity, it's not getting skinnier or wider. Okay, trajectory at which it's changing is not going to be affected. It's just moving up and down the y-axis. Okay. So now B is a different story. B is a little tricky. Up and down, up and down. It's like it's bouncing back and forth. Now this is funky. This took me a while to wrap my brain around back in the day of what is B doing? Okay. So what is B doing?
Is it moving it right to left?
It is moving it right to left. Very good. But depending upon how big and small, what does it mean by moving right to left?
Well, I know if you like move right, your B is going to be negative, and if you move left, it's positive.
Okay, so if you negate your B, you moved it to the right. If your B is positive, it's moved to the left. That seems kind of backwards to me, doesn't it? Kind of different. All right, so I'm going to try something. I'm going to make A 0 here, and I want you to see what happens. Okay. Remember how we said A made it a flat, straight line when it was 0? What kind of function do I have now if A is equal to 0?
Linear.
Ah, linear. So what is B? Starts with an S.
The slope.
The slope. Yeah. So, okay, cool. We get it now until I do this. Now we put a curve back into it. But does it still mean it's slope? Yeah, it's a special type of slope. Okay. Notice the slope at the y-intercept. Notice its trajectory right here. Okay, we can shift it up and down. That slope hadn't changed. Same thing that we've been dealing with linear functions. Okay, I can flatten the curve closer to 0, like we had earlier. Negative slope. Okay, now follow along. There's my negative slope. There's my positive slope. Watch the slope at the y-intercept when A is positive. So if I were to draw a line here, a tangent line, and when I emphasize a word here, let me clear my throat, tangent line at this point. that slope of that tangent line would be positive because you would see it's increasing at that particular point because it's going up. Would everybody agree? Now, check this out. If B was negative, and we see that bouncing effect, it bounces over. Now look at the tangent line, look at the point and what it's doing at that slope. It's decreasing. So that's why it kind of seems opposite. It's bouncing back and forth, where that B value is going to tell you what the rate of change is at that y-intercept. Does everybody follow that? And it kind of gives you a directional component of, am I increasing or decreasing at my initial amount? Here, we're decreasing at my initial amount being the y-intercept. Okay? Does everybody follow that? Is this helping kind of get that visual of why things are working and what they're doing, like these moving parts? And here's the best thing about it. I can go crazy with this, but I'm gonna stay a little centered on it. So I'm gonna make B positive. I'm gonna make it 3. Now watch what happens even if I change this to concave down. Notice that it's still increasing at the y-intercept. So if B is positive, that tells you what it's doing. It's increasing or decreasing, or excuse me, it's increasing because it's positive at the y-intercept. No matter if it's concave up or concave down, it's still going up. Now, if B was negative, it's still decreasing no matter if it's concave up or concave down. So it gives you a directional component. Okay, so let's write that up. And again, until I really just said, what if A was 0? And it was almost like a bolt of lightning when it happened. Okay, so we're looking at a couple of things. One, direction, positive or negative. Oh. Positive or negative at y-intercept. Your book will not break this information out immediately because this is more of a chapter 6, chapter 7 hint calculus type stuff. It would be the instantaneous. I can't write today. Instantaneous rate of change at y-intercept. Okay. So if we recall it's positive, it's increasing. If it's negative, it's decreasing. Because when we think, if I ask for a one-word answer on the test this week, one-word answer of rate of change, what would you say that one-word answer would be?
Slope.
Very good, Amber. Slope. Very good. So rate of change, we think slope. The slope, if it's positive, it's increasing. If it's negative, it's decreasing. Those rules still apply. We're not changing the rules for quadratic slopes, if you will, than we did with linear. Slope is slope. Rate of change is rate of change. If it's positive, it's increasing. If it's negative, it's decreasing. The higher the value, the steeper it is. Okay. The flatter, the smaller value, the closer to 0 it is, the flatter your curve will be at that particular point. How slowly it's increasing or how slowly it's decreasing, closer to 0. Okay? Does everybody follow that? Now, again, here's the bolt of lightning. And some of you may already have caught this. Like Lillian, you probably picked this up way back when, and it took me a little bit longer to figure it out. But when A 0, this whole term goes to 0. What does that function now look like? Bx plus c. It looks like the what? Go for it. Say it.
Slope intercept.
Yeah, slope intercept, which means it's what type of family of function? Starts with an L, ends with an N here.
Linear.
There you go, linear. Very good. Okay, so when A 0, you see that slope really come through. And guess what? The y-intercept also comes through pretty clearly. Now, another way we can also look at this y-intercept, more particular, especially when this is 0, is it's the only value that x is not affecting. Doesn't everybody see that? Like x is being squared, then multiplied to a. X is then being multiplied to b here. We're finding that sum. Then we're adding just this constant value. So if x was equal to 0, just like in our linear functions, okay, this goes to 0, this goes to 0, so 0 plus 0 plus c, f of 0 equals c. So my order pair would be 0, c, y-intercept. So the rules at which we find that y-intercept also haven't changed. It's when x is equal to 0. Okay. Questions on that? How do we feel about unpacking this? Again, we took what we've known as a class, and then I tried to fill in some blanks. Because now knowing these constants helps figure out some of this stuff. Okay. So let's take about a 4-minute break, because we broke down a lot of fun stuff here. And then we'll come back together and we'll look at some more properties of quadratics. All right. So when the music stops, kind of like the musical chair kind of thing here, we'll be back together. Okay, let's go ahead and bring it on back. We're going to talk about the increasing and decreasing of functions. So let's see here. Not everybody's back. Give me a thumbs up if you're back. Oh, there we go. There we go. Pop them back in. Good, good, good. All right. So I'm gonna go ahead and share my handy dandy whiteboard with you. Now, as we look at increasing and decreasing functions, one thing I want you to keep in mind is, and I will keep everything kind of up to the side here. We want to be reading our graphs from left to right. So as I talk about change in X, I'm going to be thinking X1 to X2 as it pertains to a particular graph, concave up or concave down. X1 is less than X2. So as we progress down the X number line here, okay, horizontal axis. So now, if a function is increasing, that is a parabola, or any function for that matter, as long as we know on an interval x1, x2, where x1 is greater than, or excuse me, whoops, x2 is greater than x1, as we established here, okay, the function is increasing when f of x2 is also greater than f of x1. So we know it's increasing when given x2 is greater than x1, so it's further to the right, f of x2 is greater than f of x1. Okay. Decreasing. Still establishing x2 is greater than x1, still reading from left to right. We see that if it's decreasing, f of x1 is greater than f of x2. Okay. So take a moment, write that down, let that sink in a little bit. Okay, thumbs up if you got that written down. We're going to go back to Desmos to kind of help explain some of this. Got one thumb, two thumbs. Give me an X or a thumbs down if you don't have this part written. Okay, got a couple. Good. All right, take about another 30 seconds. We'll take another sip of some great, coffee grind, cup of joe. That'll wake you up. Okay. We'll go ahead and change over here. Let me know if you can see my Desmos screen here. Okay, so the first thing I'm going to look at is the specific points. So x1 is represented as 4.1. Okay, or excuse me, x1 is going to be represented as 0. x2 is 2.167. Can everybody see that? Now, given that x2 is greater than x1, we see the outputs of x1 is higher than the output of x2. Therefore, we know this is decreasing on this interval of x1, x2. Does everybody follow that? Now, if I were to kind of shift this around a little bit, okay, we've got several points we can pull from here. We can let x1 be negative 3.167, x2 being negative 1.379. So again, this works in the negatives as well. X2 is in fact greater than X1, so that still holds true. But my output between these 2 points, my output at f of X2 is in fact greater than output of f of X1. Therefore, it's increasing on that interval. Now, some of you are going, well, it's not always going to be increasing. Could be decreasing. That's right. We look at this interval here, where my input is negative 4.95, output 0. My X2 is now taken on as negative 3.167. My inputs still hold true. X2 is greater than X1, but my output, f of X1, is greater than f of X2. I just wanted to give you a visual of that, those statements on the intervals. So that way we can pick any 2 random points, any 2 random axes, any 2 random coordinates, and see if it's increasing on that particular function. Okay. Does this also hold true for for linear functions? This property still hold true for that? X2 is greater than X1, then the output of f of X2 is greater than f of X1. It's increasing and decreasing otherwise. What do y'all think? I'm getting a yes. I agree. It does also hold true because it's based on change in output and change in input. Okay, so if we see that, and it's more or less a comparison between those inputs and outputs. If we see it larger, if we see that f of X2 larger, therefore it's going to have that positive outcome. If it's negative, it's going to have a negative outcome. It's going to be a decreasing. Okay. All right, now another important piece that I want to bring up is called the vertex. Now the vertex is important because that tells me the peak or valley. Okay. Vertex. I'm going to start with the visualization where if it is a concave down, it's the highest most point. If it is concave up, it's the lowest point. Okay. Now with the vertex, you got 2 different other types of equations that you can bring into the fold. I'm going to start with the basing f of x equal to ax squared plus bx plus c. Your vertex can be given by a specific negative b over 2a. That is your x value of your vertex. Okay. Your output would be based upon that negative b over 2a. Okay. So where your coordinate's going to look like negative b over 2a, comma, f of b, f of negative b, excuse me, over 2a. So the vertex is going to be telling you location where it's at and what the actual amount is. This is the coordinate at which your vertex is applied to. So there's negative b over 2a. This amount here, f of negative b over 2a. Being able to find the vertex tells us how high something is or how low something is. So here we have we'll call a max. Here we have a minimum. You could have a maximum or minimum depending upon what your parabola is. Now, if a is equal to 0, probably not going to have either unless you're on a closed interval. Okay. The other form, or let me say one other thing. You also notice with parabolas, these parabolas are symmetrical to where you have corresponding outputs. So the same value based on a given input. But that line of symmetry or axis of symmetry is about that x value of your vertex. Okay, so if you can find that vertex here, you're going to be able to know where the maximum minimum are located and also where the axis of symmetry is. Okay, minimum works the same way. Let me pause there. Thoughts, ideas, feelings about it? I'm gonna put a big old star by this one because in the business world, we want to know where we're maximizing profit, revenue, minimizing cost. So it's going to be good to know how to find those peaks and valleys. Okay. Other little piece with the vertex I want you to look at is an actual vertex form, where the form of the equation is centered around, excuse me, fix something here. Do that just a little. There we go. Sorry, I had some technical difficulties there. So we can create a form about the vertex where everything is centered on the vertex. The ax squared plus bx plus c form is based on the concavity, rate of change, and y-intercept. So you don't see that come through as much on this form where it's only really looking at the vertex itself. Okay. So we see that form a times x minus h squared plus k, where h and k are your vertex components, where h is your x value, if you will, and your k is your output for the vertex, the f of negative b over 2a, where h is your negative b over 2a in the other form. Okay. It gives you some little indicators as well. The parabola opens upward if a is greater than 0. No, that hadn't changed. But it also still tells us that there's a vertex at a minimum, which we just noticed. Same thing with if a is less than 0, we're dealing with a maximum. Okay, which means it's concave down. So that hadn't changed. But I wanted to include that with this other form to show you that the rules of A have not been affected. A is A. A is still going to tell you concavity. A is still going to tell you the closer to 0 it gets, the wider it gets, the further away from 0, the tighter it gets. Okay. Pause there. Think through this one. So you'll need to probably be able to think through both these forms. I personally like ax squared plus bx plus c, just because to me it's more useful because you can see a lot of different things. Very similar to slope-intercept form, and I'll let Lillian kind of weigh in her opinion on it. But it's very similar to slope-intercept where it gives you a lot of pieces of the puzzle point blank right there, and you can interpret a lot just by looking at that form. Lillian, do you want to add anything to that or disagree with me? And you are perfectly fine to disagree with me on that.
No, I like it. It's just a little bit more complex, but it does give you a lot more information.
Yeah, I agree. I really think so as well. So one thing students like to also know is, okay, what if I'm given vertex form? Could I potentially get it to standard form that we'll call it? That is very, very true and very accurate because you can also see what H and K and where that piece goes once you're dealing with it in a different form. So for example, let me share a new screen with you. This is where we're going to start getting in more of the nuts and bolts of multiplying out and some of the tools that we've been using here. Okay, so we have vertex form. And if I wanted to go to standard form, what we're going to have to end up doing is multiplying this out and then combining like terms. Now this is going to get a little squirrely, so just hang on, okay? We are going to, and I hate using this word, but it's the word that we all know. If I say FOIL, we know, oh, first, out, enter, last. It's distribution. And I'm going to rewrite it showing that distribution piece here. Oh. We're actually multiplying out that binomial to itself. And then we multiply the x's. So x times x is x squared minus xh minus xh plus h plus k. So we see the x squared term come into play here. We have a times x squared minus 2xh, since we have those two here, plus h plus k, distribute. We have ax squared minus 2axh plus ah plus k. And believe it or not, we are in, Leon's looking at going, oh no, 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 no. Believe it or not, we have it in the standard form. You just got to know what you're looking at. Okay.
You forgot to square your h.
No, I did not.
Negative h times negative h.
Yeah, it's right there. And then h squared. Don't know what you're looking at, Lillian. I completely missed it. Lillian, thank you for catching me. Okay. So you can manipulate this a little bit. First of all, is there an x term at all within these here? There is not. So that takes on your c. That's your y-intercept. Okay. This one's pretty straightforward. Your a is a. Okay. This one, however, it's always the middle. The middle is the tricky part. I would need to do some maneuvering around, but the negative 2a times h is your b. Okay. And there are places where knowing what, in terms of h and k, how that affects and what it is in terms of standard form allows it to make it a little bit easier. But again, and this is where we're going to probably kind of capstone some of these main talking points. A concavity is solely based with that x squared term. We see that come through here. Your a and h, really focus in on how my function is changing at that y-intercept. Notice that k is nowhere near this piece. There is no k here. The k, because our k represents the output. That output is solely being focused on in right here. Okay, well, the output does have some impact on where it is on xy's, and also how A is making the concavity, how wide or skinny it is, but also where the y-intercept's at. Okay, so it's a little tricky, and that's where a lot of students like, boom, this. Okay, now this is harder to go to this point. We have to do some completing the square to go from standard form to vertex form. I'm not so worried about you going that way, but just knowing where some of these pieces are within vertex form. Okay. You need to be able to look at vertex form and know, okay, what's the concavity? What's the concavity? A, it tells you that. Okay. Where's the y-intercept? That may not necessarily be as apparent. Okay. That may not necessarily be as apparent. And let me pull up the example I had up here a second ago, where historically students go, oh, it's K, boom, done, moving on severe. Not so much. Look here. There's my K value. Can everybody see the shared screen? Yes. There's my K value. There's my H value. Look what's up here. My y-intercept's up here. So K is not, in this case, the y-intercept. Okay. How wide it is, and how skinny it is, dictates that. We share another screen with you. I'm all about sharing screens today. But I think it helps as we are able to move some stuff, especially with Desmos here. We got that pulled up for us. Let's make it a little bit, no, you know what? We're gonna make it nasty and ugly, as they say, with our values, because that's what you're gonna get on the test. So there's my K value. Negative 1.917. There's my H value. There's my vertex. So if I wanted to build this vertex form, we can easily do that. We would negate my H value, so it'd be plus, okay? We would subtract, so K would be negative or minus 1.917. Multiply it by A. A is what we don't know. We would have to solve for A. But notice that my K value is not where the y-intercept is. We would have to multiply what A is by H squared plus our K value. So it takes a little bit of work to get there, but just know that K is not equal to your y-intercept, unless my y-intercept and there we go. The K value is the y-intercept if in fact the vertex is on the y-axis. And that's a pretty important piece. Okay. So now let's look at a question together. Let's look at a word problem. With all this fun information we've learned today. So using data from 1900 projected to 2020, the percent of US population was foreign born can be modeled by the equation here. Okay, where X is the number of years after 1900. All right, I'm gonna pause this and I want you to look. I want you to tell me what you know by looking at that equation. What can we tell from this equation? Is it concave up or concave down? What do you think? You can use the chat to throw it to me. Okay. I've got two answers from George and Ivy. What's everybody else think? This is part of your participation and your attendance. There we go. There we go. Up, up, up. Why do we know it's concave up? Because the value is what? Starts with a P. That's what I'm looking for with this.
Positive.
Positive. Very good. Okay. All right. What's my y-intercept? What's my y-intercept?
Positive.
Positive. Okay, very good. What is the actual value for my y-intercept? Emma's giving me 18.9149. Very good. So that's the initial amount. During what year? During what year? I will take two different answers here. We'll have to be able to tie these up. Chloe's giving me 1900. Very good. That's the preferred answer. If somebody gave me when X is equal to 0, that's also appropriate. But keep in mind, when X is equal to 0, that's year 1900, as given by data from 1900, where X is the number of years after 1900. Very good. Okay. Tough question. Probably a 75% miss rate on the final exam. This is the type of question here. The B value tells me what? What is the B value telling me?
The slope.
The slope at what point? This is tricky. Slope at the y-intercept. Very good. So tell me what the population is doing at the year 1900. Now, again, let me restate this. Listen to the words that I'm using here. Tell me what the population is doing at the year 1900. Is it increasing or decreasing based on what we're finding with that slope?
Decreasing.
It's decreasing. Very good. I heard Amber say it. And I got it in the chat from Ivy. Thank you very much. So we're able to extract a lot of information just by looking at the numbers. And that allows us to kind of set our frame of reference and start wrapping our brains around a picture of that parabola that's concave up, that has an initial amount at 18.94, that's decreasing at that initial amount at a rate of approximately 0.3692. Okay. So everybody kind of getting a feel for that. Now that that 18.9149, I'm going to throw on a limb and say, you know what? That's percent. So 18.9%, that is decreasing by about 0.4% per year. That is a unitized amount over one. Okay. How many of you, and you can do me a blast chat here, or chat blast, there we go, of if you could do exactly what we just did by yourself on the next test or final. Okay. You can say yes, no, or maybe. Yes being yes, without a shadow of doubt. Maybe, you know, I could get most of that. No, there's no way I could even recognize the A value concavity. Tell me what you got. Can get a lot of maybes, and that's good. Maybe I'm good with maybe. If you threw a yes up, I'm good with that as well. To me, if you can do that, you eliminate a lot of extra work. Lillian, what do you think? Chime in here. What you think?
I think a maybe at this point is pretty good.
Yeah, absolutely.
Yeah.
Absolutely. Okay. So during what year does the model indicate the percent of foreign-born population was at a minimum? So we can look at graphing this and find that minimum value. Okay. The fact that this A value is very close to zero, you're going to look at a very flat looking parabola. And that decrease is also very minimal. So it's going to be a very flat, steady decrease. It's going to take a while for it to hit that minimum. I'm thinking decades long to meet that minimum percentage. Now, you can take your B value, and I want you to try this on your own. I want you to take your B value and find what year that occurs. Negative B, so negate this value, divide it by 2 times A. On your own, try that real quick. Take about a minute to do that. If you get done, try to also find what year, excuse me, what that percentage was, which is part B. Negative B over 2A. Tomorrow we'll derive that negative B over 2A specifically. Okay, go ahead and throw it up in the chat, or you can give it to me verbally. What year? You can give it to me the 2 decimal places, that's fine as well. If you have no clue where to start, I can bring up the whiteboard and I can help you kind of get going in that direction as well. You can send me that direct message or just say, you know what, I'm not sure what I'm calculating here. Amber's point blank saying, whiteboard, let's do it. Just need one. Okay, Chloe's throwing up a number. She's saying 1968. Let's find out. Let's confirm or deny Chloe's answer. Okay, first of all, as you saw a camera of one of my kids' toys that I put on the desk. We tried to clean up yesterday and they don't do a good job cleaning up. That's all good. We're 5 and 6. It's kind of to be unexpected, right? So my equation is 0.0027 x squared minus 0.3692x plus 18.9149. So this is my B. This is my A. This is my C value. My vertex is occurring at negative B over 2A. So that's going to be negative times negative 0.3692 divided by 2 times 0.0027. So we get that little tricky negative piece here. That could be a little problematic. But you think, oh, it's already negative. I don't need to negate it. No, we want to negate it because if I understood my function correctly, it's going to be doing something like this, which means this x value minimum is going to be a positive value. Because if it's decreasing that initial amount of 18, and it's concave up, it's going to land somewhere on the positive x side. So again, kind of use those numbers to project where that minimum is going to be. We'll use the same idea to project where the maximum is going to be as well on a profit function or revenue function. So if I do this, I get 0.3692, and I'm going to be very as exact as possible. So 0.0027 times 2, 0.0054, and 0.03692 divided by, this is giving me approximately, I forgot a zero, sorry, in my calculation, but it is going to be approximately 68 years. So 68 years after 1900, so 1968, Chloe, spot on. Very good. All right, nicely done. Amber, did that help?
Yeah.
Very good. So if I do another share with you. Can you see the Desmo screen? Are you seeing the Desmo screen? Yes.
Yeah.
Okay. So there is my graph. I did it in terms of decades. There's my y-intercept, 18.915. So it rounded it a little bit. There's my minimum occurring, and it also gives me that percentage, so we can go back and calculate that in. So the minimum percentage of foreign-born, US that are foreign-born, is 6.294. So we see it bottom out at that point. Now, beyond that, we see an increase where here's year 2000. 2021 is right here, halfway between, so there's where we would be. So if we were using this current model, there you go, a little bit more like that, there we go. We're saying 13.88% of the US population is foreign born. That's how we would interpret for our current year. Okay. Thoughts on that? Questions, comments, concerns? All right, I'll tell you what. I hit